So I'm going to talk about the impact of community codes in astrophysics. So Catherine and Anshu really set the stage today nicely with some of the nuts and bolts that go into architecting community codes. What is a community code? How do you do a community code well? I'm going to really look at some case studies of community codes in a very specific domain of astrophysics. A lot of it's going to be colored with my own experience, and I've tried to be inclusive, but you can't do an overview of the entire field just in one talk like this. So if I've left anything out, let me know. And this is an important topic to me because I've had an enormous amount of impact of community codes on my career and in my life. And I started using a community code Flash as a grad student, and I still use that code today. It's a very different looking code. My experience and my use of that code is very different from when I started, but it's something that's very important to me. So I would say that the impact of community codes cannot be overestimated in astrophysics. Certainly I owe my career to a community code. And there's enormous benefits of using community codes in astrophysics and science in general. I think open source is a good thing for science. I think it reflects the ideas of open science. I think it gives a pathway to reproducibility, which is also extremely important in science. If your code is open, if it's a community code, I can publish the things like my parameters files and my input data, and maybe somewhere out there, someone can reproduce my results in a paper. Sometimes that's realistic and feasible, sometimes not. It's also extremely important and a huge benefit of community codes that you don't need to reinvent the wheel. If you've got a new problem, there might be a code out there that you can start with to get to a solution much, much faster than you would have otherwise. And that's good from a scientific perspective. It's good from a production perspective. You get the answer quicker. But it's also good because we're not wasting money on development that's unnecessary when there's a perfectly good tool out there that you can use and reuse. So you get more science per funder dollar, I think, out of community codes. And as a methods developer, you also get a greater impact from your effort in developing a new method or a new tool or a new code. You put it out there, someone else uses it, and these things can take off that way. And I think that's a tremendous benefit as well. And hopefully from a community code, you might end up getting better documentation. But I put a question mark by that. Now, community codes are everywhere in astrophysics. This is by no means an exhaustive list of community codes in astrophysics, but these codes do a lot of different things. Most of them are simulation codes at their core. But these days in astrophysics, we're not just doing simulations with community codes or large-scale computing. Even observational astronomers now really are bordering up to high-performance computing needs for their data science and the data analysis. It's big data. And there's many different codes in astrophysics that are observationally oriented or data analysis oriented that are not strictly high-performance simulation codes, like a lot of what I'll be talking about here in my talk, and I think what we've been talking about in general in the program. And you can go to this wonderful thing called the Astrophysics Source Code Library. And on there is a list of over 800 open source codes that are in some way astrophysics related. Not all of those what I call a community code, which Anshu and Catherine touched on this earlier in their talks as well. What is the definition of a community code? I don't think it's just an open source code. There has to be an installed and embedded and an invested community of users and developers that keep that code going. So I can write some code and I can put it up on GitHub or I can put it on ASCL or wherever I want. But that's open source, but it's not necessarily a community code until there is a group of people that's invested in that code and seeing that code continue, be successful, and be used. So I think that restricts the number of community codes in any field, and astrophysics included. I think community codes have a tremendous amount of impact relative to proprietary and closed source codes. So what I've put up here, and this is very approximate, twiddles in front of all of these numbers, is a breakdown of the approximate number of publications for a few of the most popular community codes. Topping the list is the code Gadget, which is for structure formation and galaxy formation and in-body calculations of dark matter particles. Roughly maybe 3,000 publications credit Gadget or use Gadget in some way, often directly. It's enormous. Zeus, finite different hydrodynamics code, been around a very long time. About 1,000 publications have used Zeus. Flash, code that I use, where Anshu worked for a long time, about 800 publications directly make use of Flash. Enzo, another finite volume code, 400. MESA, which is a very new code, In stellar astrophysics and stellar evolution, we're talking, in 5 years-ish, 300 publications directly using that community code. So community codes have an enormous impact, much more so than proprietary codes, generally speaking. So why? Why are community codes popular in astrophysics? Well, there's practical considerations like monetization is unlikely. Most of the things that we're doing are not very practical. Private industry is not looking to simulate supernovae, it turns out. I've looked. Often also, the problems are complex, and it's extremely difficult for the lone coder to go out there and write a code that does an interesting problem, that can tackle an interesting problem. It takes a long time, many person years of effort to build some of these codes. And I think communal coding leads to a greater return on that investment. Just like we saw earlier in the previous slide, there's a lot of publications per community code. And that's because you're building incrementally. You're taking a code base, which is useful, adding some new lines of code, treating a new problem, and I think you get a lot more return on investment that way. So it's popular in astrophysics. There's also benefits to this. The more eyes you have on your code, the more likely you're going to find your bugs. All right, and we can get into what do you define as a bug. I like Anshu's definition, but there's also the practical definition of bugs that might not have a giant impact for your particular problem. Right? Maybe there is a bug in the code, but it's not really affecting your application. But someone else takes that code, tries a new application with it, and this bug becomes apparent. And it shows itself, which goes to Anshu's point about unit testing and having a testing matrix, right? Because there's all these different use cases that you can have for a community code, and your particular topic of interest might not expose these bugs. But putting it out there, letting other people read your code, letting other people see your code and use your code, they might find use cases where problems show up. And then you can fix them, and you should fix them. And that's the other point. Testing is more rigorous. And this is either direct testing, like what Anshu was talking about, where you have a matrix, you do nightly regression tests. It also is real-world use cases. Someone actually tries to use your code to do a new simulation, and they find a bug. So astrophysics is a pretty complex field. Often the simulations that we're doing have multiple kinds of physics baked into one application. From compressible hydrodynamics, magnetic fields, radiation is important. Most of these things are self-gravitating. You also get into fluids that have complex chemistry and nuclear burning. Multi-fluids, where different fluids in the same mixture behave differently. Complicated equations of state that cannot be expressed analytically. General relativity, special relativity, many other things. So most astrophysics problems are not any one of these things. They're subsets of groups of these things. And so they're complex. And mathematically, that's a lot of different kinds of models that must be used to solve these problems, from hyperbolic to elliptical to parabolic PDEs, many stiff equations and ODEs as well. So it's complex both physically and mathematically, and we have to use different mathematical models to solve these problems. So that's on the physics and math side, but trying to tackle astrophysics problems with their multiphysics complexity and their multi-scale complexities introduces big infrastructure complexities. And this is where people like me, an astrophysicist, we get out of our depth. I'm not a computer scientist, I'm not a software engineer. I know the physics, but this is where things get a little fuzzy for me. And the problems that we face in astrophysics, there's an extremely high dynamic range in both space and time. And you've got to address that. And the way to address that is with a good infrastructure. Often we use adaptive mesh techniques. And then you get into problems that are big. Astrophysics has big problems. And we need extreme scale to tackle these things. Things like structure formation, things like supernovae, can only be addressed with high fidelity at some of the largest scales in computing that we have. So you've got to have the good infrastructure, things like input, output, and grid, the build system, and analysis tools to be able to do that. And no lone coder can really do that with skill and with the kind of level of accuracy that's needed to be scientifically useful. All right, so some of these things that go into the infrastructure complexity. I mentioned adaptive mesh refinement. It's a pretty common technique in many classes of astrophysics problems. Of course, it's not everywhere in astrophysics, and nor should it be. But this introduces a lot of necessity for things like prolongation and restriction of the data, ghost zone filling. This is all enormously complex on parallel architectures. Fine coarse boundary flux correction, and then parallel load balancing, which is critical. So this can be a lot of work for any individual to do. It can be a lot of work for someone who's not an expert in software engineering and code design, i.e. most astrophysicists. Input-output is also really complex. And writing to disk from 100,000 processors is way beyond me. I wouldn't know how to do that correctly. And the typical astrophysics problems, from my personal experience, we're talking of hundreds of terabytes of output for a project, and each write to I/O to disk might be hundreds of gigabytes per write. So that's complex. That's a computer science problem that is beyond me. And what we found just in my experience is that you can get big savings from making machine-specific tuning to just your I/O system. So this is really getting into the guts of writing the I/O, knowing the system architecture that you're running on to tune the performance in a way that doesn't completely stall your calculation. Another very important infrastructure tool that we often use in astrophysics is particles. And these can be used for Lagrangian tracers that just move along with the flow in a way that's gathering useful data. They can be active particles, things like dark matter particles, Anshu mentioned earlier, that actually gravitate and interact with the fluid through gravity. Also things like laser ray tracing and ray tracing calculations in general, and also fluid structure interactions. You can put an embedded boundary that moves along with the flow that is tracked by particles. So those are infrastructure things. Any question about that? I'm going to move on to a specific example case to kind of make this a little more apparent, and that's Flash, which is the code that I use primarily. Flash is a multiphysics simulation framework which has been applied to an enormous number of different problems, not just in astrophysics strictly speaking, but in computational fluid dynamics in general. This is just sort of the family photo of many different calculations and results that have been gained with Flash. Flash was originally for thermonuclear burning in degenerate stars, things like classical nova bursts and type 1a supernovae. It's expanded to many, many other problems in astrophysics, as we saw on the previous slide. But when I had approached the problem of core collapse supernovae, it had never been used for simulating the mechanism of core collapse supernovae, which is what I was interested in. And so, I was able to take this enormous code base that had already in it things like hydrodynamics and gravity and the adaptive mesh refinement and the input-output and all this huge suite of data analysis and visualization tools. And I, as an astrophysicist, could focus only on the things that were interesting to me and necessary for me to address the problem that I was interested in. For me in particular, it was things like a very complex equation of state to describe nuclear matter and neutrino physics, which are critical to core collapse supernova mechanism calculations. And this talk isn't really a science talk, but what I was looking at, core collapse supernovae are the deaths of massive stars. You basically get a big star that collapses at the end of its life. It forms a neutron star and causes an explosion. But we didn't understand how that mechanism works. We really still don't. So it's a big major problem in computational astrophysics, and this is one that's really pushing the frontier of computational astrophysics. You find this kind of problem running on the largest scale computers even today. And 3D is something that was very hard to push to. And so I was able to take Flash, this tool, and really working by myself in a couple of years, completely adapt it to address with pretty high fidelity the core collapse supernova problem. And this is a task, a technical challenge that had taken whole groups of researchers a few years, really several years, to accomplish. But because I was working with a community code, one that was so well developed, one that was so well designed, and so full-featured, I could do it working feverishly by myself, pretty much, in a short period of time. And this is one of the results. I got to have some eye candy in a talk like this. But this is a 3D simulation of a core collapse supernova done with Flash just a few years ago. And this is a volume rendering of entropy. And that's the other thing. I mentioned data and visualization tools. I didn't have to write my own data and visualization tools. This is actually made with Visit, which is a very widely used visualization software. Visit has a reader for Flash. I didn't have to write that. I just have to use it. And so that right there is time savings as well. So this is what you can do with Flash in 3D. and that's actually neutrino-driven convection there, causing buoyant plumes. The shock surface is actually the blue. What happens in these things is the shock tends to stall, and then the neutrinos revive it and push it out. This was run on MESA. And this was an early simulation in our program on MESA. And since then, we've actually started an InSight program looking at MHD turbulence using Flash on MESA. And I just flashed this up here because it's a very short lead time to go from we don't have a code to address this problem to we're now running an InSight project on one of the biggest machines in the world. And that's because we leveraged community code. There's no way I or my group, my team, could have done this starting from scratch. And all of that work that went into the infrastructure of Flash from people like Anshu and Catherine too, leads to a very well-performing code, one that happens to be fairly tuned for MESA. And this is just a weak scaling plot from one of our production simulations of core collapse supernovae. And we've showed pretty good scaling, all the way up to about 500,000 cores on MESA. And, you know, I'm very proud of this plot, but it's not all my doing. It's mostly the doing of the experts in software engineering that helped develop Flash. And I could take this and I could say, can I run at this scale? Well, yeah, I can.
That animation you just showed, is that using finite volumes?
It is finite volume. That's correct. OK, so this is a specific case. But Flash is special. It's been well funded for the development of this code for almost 20 years. It was designed by professionals in their respective domains. Right? 1997?
That's what they're laughing about.
Yeah. 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 So professionals like Anshu and Catherine designed this code to be, you know, a well-performing code, to adhere to standards that are strict, and to be flexible, to be adaptable, to be professional code, unlike what an astrophysicist like me would sit down and write. It's special because there's been a core group of developers in a central location working with each other to maintain, develop, and extend this code for a long time. Most astrophysics codes are done on the cheap, meaning there's no explicit funding for the code development. They're funded to do the science, but they need a code to do the science with. And so they have to write that code in order to do the science that they're funded to do. So Flash is special. An example of a code, which is a very successful code, which is funded on the cheap, is Enzo. Yeah?
So you showed the plot for weak scaling.
Yeah.
Do you have like the results for strong scaling?
Yeah, I do.
Okay.
It's not in the talk.
So like how many nodes is it strongly scaled?
It depends on how you do the strong scaling problem, but what I've basically gone down to is 128 by 64 by 64 grid zones per MPI rank, and that rank is using 8 threads. So on MESA, that's technically 2 cores. So per core, it's down to 64 cubed. And I also have the thread-to-thread speed up, and there's a reason 8 is the number of threads I use. OK. So Enzo is a code that's actually fairly similar in methods to Flash. It's a finite volume code, uses basically the same kind of finite volume techniques. It also has active particles for dark matter. You're actually seeing a dark matter simulation right here with Enzo. It does MHD, it does some radiation, heating and cooling, which is very important to structure formation. But Enzo is one of these codes that has been developed really in a distributed fashion. There's no central group of developers. There is about 12 core developers, but they're in very different locations. They make heavy use of online collaboration and distributed version control. They have very good standards, but Enzo is not a code that has been architected from the ground up by professionals. It's good code. And it's a code that's been extended to treat many other problems besides the core problem that it was designed for. But it's a very different model. Still a very successful code. And they've had an enormous impact. Over 400 publications in the area of galaxy formation and structure formation. And out of Enzo, another community code project was started. and this is called YT, and it's a data analysis and visualization project. It's primarily Python, but there's actually C under the hood, so I say it's glued together with Python. And this grew out of Enzo to be Enzo's sort of data analysis and visualization tool, but since then it's taken on a life of its own, and it really has been applied to many other codes, Flash included, are now compatible with YT. And I think it deserves acknowledgement because they have an amazing developer community. Again, no centralized development, it's all distributed, enormous interaction online, and project's pretty impressive. And they have a huge impact, I think, because they're making things like accessing your data and doing hardcore data analytics with adaptive mesh refinement data a lot easier than it used to be. That by itself is a tough challenge to come up with a data analysis framework for some of these data sets. And by being so compatible with the broad range of community codes in astrophysics, YT is already having a huge impact. Now there's areas of astrophysics where community codes are not the standard. And I'm just calling out a couple here, stellar evolution and radiation transport. There's not a lot of community codes dedicated to these two areas of astrophysics, and they're two areas of astrophysics that are very important. I think there's a lot of reasons for why community codes don't tend to be popular in these two topics. One is that this is very complex stuff, and so the codes tend to be themselves very complex. They represent a lot of effort on the developers, and I think there's some ownership where people don't want to let that go. They also tend to be spaghetti code. So I don't know. But just as an example of why this can be a bad thing and why we do need community codes even in these areas, massive stellar evolution, which is very related to what I do, was basically a one-shop problem for a long time. There was one code and one group that were producing massive stellar progenitor models, which basically are the initial conditions for the type of simulations that I do. My entire community was using for initial conditions the results from one group and one code, because that's all that was really available for what we needed. And we trusted them. And we should. They're good. But we didn't have a lot of flexibility in that. Then along came a new code called MESA. And MESA stands for Modules for Experiments in Stellar Astrophysics. This is a community code, open source, started primarily with one principal developer, Bill Paxton, who's a very interesting guy. He's retired from Adobe, and he has patents for PostScripts and like PostScript, like what printers use. He holds a patent for that. And Bill decided that he was interested in astrophysics and wanted to write stellar evolution code. And so retires from Adobe. That's what he does now, which is really interesting. He's an amazing programmer, naturally. But there's no stick that you can hold over Bill. Bill does what Bill wants to do, and he does it how he wants to do it, which is fine because he's actually very good. But it's just a very interesting development model. And since Bill has written this code, it's grown into a very large, active community. And I showed earlier, over 300 publications already are referencing MESA as having used MESA. And I think that paper came out in 2012 or 2013. So just in a few years, this code is having an enormous impact. And I think that's showing, one, the quality of the code, but two, also the need for a community code in this area of astrophysics, where for decades we didn't have a community code. So this is enabling people to go and do new problems and do new things that previously weren't possible because they couldn't sit down and write a code like this on their own because it's too complex and it's too hard. But now there's community code to do it. And I think that introduces a lot of fun stuff, some of which I've gotten involved in. So one of the things that we did is we took MESA and we said we can now ask different questions about stellar evolution and about supernovae. And so we ran our own initial conditions with MESA, basically like our initial condition generator, and did some new simulations related to core collapse supernovae. We basically took where we were starting before with our initial conditions, wound the clock back a couple of minutes, which doesn't sound like a lot, but when you're simulating 1 second at a time, it is a lot, and said, does that change the problem? If I start with three-dimensional initial conditions in my supernova calculation, does it matter? And it does. And this is actually the radial velocity from that simulation where we simulated the final 3 minutes of the life of a massive star. This had never been done before. This was always just done in 1D, treated spherically symmetrically. But what we found, and what everybody really knew but hadn't demonstrated, is that these stars aren't spherically symmetric at the end of their lives. And what wasn't known is that this makes a big difference for my physics, for my core collapse supernova simulations. This was only possible because we combined two community codes, MESA, this new code that allowed us to do the stellar evolution calculation, and then Flash. It's a complex problem, and there was a reason it hadn't been done before. It takes community codes. Now, there's some pitfalls to community codes, one of which, if you make the code too easy to use or too stable, everybody will use it. That doesn't sound like a pitfall until you meet all of the users that might use your code. An example of this is Gadget. Now, Gadget, an amazing code, probably undisputed, has had the biggest impact of a community code in astrophysics. 3,000 publications, twiddle, right? It's enormous. It's an in-body and smooth particle hydrodynamics code with various heating and cooling. The development of Gadget was very centralized, developed primarily by Volker Springel, but made open source. So the thing about Gadget is that it is easy to use, and it's stable. The thing doesn't seem to crash, and it's open source. So you do get the enormous impact on the community. People can take it, they can twiddle the parameters, they can run a simulation, they get a result, they write a paper. But this is great until you find a problem with the underlying methods, which is what happened. So the original implementation of the smooth particle hydrodynamics was found to have a deficiency. It's not a bug. It's just that the algorithm wasn't quite suited to the problems that were being addressed. It turns out that SPH basically manifests an artificial surface tension. So if you have a blob, it tends to stay together more than what the grid codes was saying it should, because there was this artificial surface tension holding things together. Now, great. It was identified using code-to-code verification, which is something Catherine mentioned, very important. So in a big code-to-code verification project, it was found that SPH behaves differently than every other code and behaves differently than we should expect the physics to behave. Now, the fix for this was actually easy. It's like a two-liner, all right? And it removes this artificial surface tension from SPH. Great, awesome. But the thing is, the distribution model of Gadget was Volker Springel writes the code, gives you a tarball, and you go do your simulations. There was no real good method for pushing this fix to all the many, many users of Gadget. And so many users didn't implement this fix. And even to this day, people are publishing papers using the unpatched version of SPH. Like stage fright. Anybody have an Android phone? The apocalypse is coming. The other thing about this distribution model is that it led to a lot of different proprietary versions of Gadget. So Gadget was released basically as SPH and in-body, but in order to do anything interesting in galaxy formation, you have to have a lot of other physics, microphysics, that go into the calculation. That wasn't made publicly available, and so lots of other groups wrote their own. And so you have all these disparate versions of Gadget, which, they're all called Gadget, but they really do very, very different things. And so that can be a pitfall as well. I don't mean to pick on Gadget. It really has had an enormous impact in astrophysics. So you get code divergence or balkanization of the code. That can be a pitfall in community codes. And it takes professionals, it takes a community making the effort to prevent that. An example was Enzo. Enzo, it's distributed. There also became this balkanization problem where many different branches of Enzo existed at different places with different groups. They were doing a lot of different kinds of things. But then they decided, let's merge it all back in. And that was a major undertaking for them to do, and it was a concerted effort, and not everybody was 100% on board. Some people had to be chained to a computer until they fixed all the conflicts. So it's very easy to have that kind of creep in a community code, and it takes a lot of effort to bring that back together. And this can be a problem in all development models, distributed, centralized, whatever. This has been mentioned, some pitfalls, assigning credit. How do you do it fairly? How do you give the developers their due? And codes really should be thought of as instruments, much like people building instruments for telescopes in astronomy, for instance. And the builders deserve credit, and it's just hard. It's hard within the traditional academic mechanisms like publications and citations to assign that credit in a way that's probably fair. That's changing. Anshu's mentioned that there's, I've got 10 minutes, that there's journals now that do focus on things like coding and implementation and methods, and that's good. Okay, I've got plenty of time left then. Talk a little bit about the future. Catherine mentioned that hardware is getting more complex. It's not getting less complex. It's not even staying the same complexity. It is getting more complex. And so today's astrophysics codes might be living on borrowed time. We're running well on the fastest computers today, but that might not be the case tomorrow. It certainly won't be the case at the exascale. So our codes need to have portability, and things like abstraction, like what Anshu was mentioning, might be critical. And task-based parallelism, probably going to be critical. Our codes don't have that today. Certainly, my code doesn't have that today. And in order to do that, you're going to need the professional level architecture and design in these codes in order to run at the largest scales of tomorrow. The problem is, and this has been mentioned already too, funding for professional code development has not been going up. And that's going to be an issue. I don't think there's any way to reach the exascale without dedicated funded efforts in code development. And there might not even be a way to 100 petaflops without it. So say nothing of exascale. I don't have any answers for that. It's just a plug. And another plug, one of the ways that we're addressing this issue, the future of computing, and staying at the cutting edge of both hardware and software and methods at Michigan State, we're starting an entire new department in computational math, science, and engineering. So this is going to be a big department, 30 faculty. I'm one of the first faculty in this program. And it's an interdisciplinary program between applied math, mathematics approximations, computer science, and then actually domain modeling, things like physics, astrophysics, like what I do. And so CMSE is sitting sort of at the junction of those three fields. And the whole point is to combine knowledge from those various domains and pursue computing at the largest scale with the best methods to tackle science problems going into the future. Yeah, that's actually about it. Any questions?
Does Flash tell you, is it built on Paramesh? And if it is, how do you deal with Paramesh not being supported anymore?
Well, she's still working. Paramesh is the grid, the AMR grid for Flash. And Paramesh does work well still on Mira. It is not built for a heterogeneous architecture. And so that is something that we're going to have to address. Absolutely. We don't have an answer for that. Paramesh is basically static code. We do make changes to Paramesh within Flash. We have a development version of Paramesh, basically, that we do push back to the Paramesh developers, where we make tweaks to make sure that the code still works and runs on the architectures that we're interested in. But we have to deal with that. We don't have a solution. I don't have a solution yet.
Or rather, we know how to do it, but we can't get funding to do it.
That's the answer, yeah. Yeah?
Do you have any difficulties with building those codes?
Do I have any difficulties with building those codes?
Yeah, on the big machines like that.
Sure, absolutely. XL Fortran is a very finicky compiler. Yeah, and one of the things about using a community code like Flash is that what Anshu mentioned. There's regression testing and there's testing on a huge variety of platforms. So, Anshu didn't go into this too much, but Flash is tested on, GNU on Intel, GNU on AMD, GNU on, do they make other processors? I don't know. But different flavors of Linux, different compilers, PG, XL, all of these things go into the test suite of Flash so that if there's a change in the code that breaks the ability for the code to be compiled on a given architecture, that's flagged as well. It's not just changes in the code that change the answer, it's changes in the code that might change its compilability. And then when a new architecture comes out, yeah, it's always a challenge to get a complex code like this built on a new system. Flash is primarily Fortran 90 and C++, or C. And so most of the time we're able to access a compiler that's compatible, but we also use some Python in Flash. And so not all systems might have the right version of Python. That can happen. Yeah.
How can you deal with that?
Banging your head on it. At least in my experience. I'm not very crafty. I just bang my head on it until it works. Flash is a fairly portable code, but it definitely takes some legwork. You have to build your makefile in a way that the system likes it. And you've got to point to the right pieces of code. Sometimes for me on different architectures like BlueGeneQ, you have to rebuild things like HDF5. I have a custom version of HDF5, which is the data format that Flash uses, that I found easier to build against than what was available on BGQ at the time I was trying to build Flash. So sometimes it does involve that extra work of this library dependency I have, either the supercomputer doesn't have it, or the version that's on the computer is not what I need. And so you build it yourself. So yeah, it can be a lot of work sometimes. But Flash is actually fairly portable, and it's because of all the effort that went into designing the code and the people that are maintaining the code and testing the code on different architectures. But that, in my experience at least, that's something that's extremely code specific. How easy is it to build on different architectures? And that's to say nothing from running. So you can get something to build, that doesn't mean it's going to run right. Yeah?
I was wondering, how do you deal with the portability issues when you need to make specific decisions to target architectures on a high level?
Yeah.
Especially
How high
lead
level?
communication framework may be entirely different for BlueGene than for a vanilla.
We dodge. Mostly we just dodge the question. So I mean, for instance, heterogeneity, right? This is not something that we've really at least I, and most of these answers, by the way, are speaking from my own personal experience. Not really something that we've dealt with head-on in Flash is heterogeneity and the use of accelerators. There is some use. There is some work on applying accelerators to things like nuclear burning networks. But really, we tuned our code to work on MESA. That was the next big machine that Flash was really targeted at performing well on. And so that's the model, and that kind of predicated the choices that would be made at a high level of the architecture of the code. For us, primarily, that meant that we were going to have to expose more parallelism in the code and use threads. Prior to the introduction of MESA, Flash was purely MPI. It was message passing all the way. And that wasn't going to work on an architecture like MESA. So there we needed more parallelism. We threaded the code. That was the big architectural change that we had to, the choice that we had to make. But we haven't, really dealt head-on with heterogeneous architectures.
So will these decisions not affect negatively users of just vanilla Linux clusters if you tweak the code for the big machines, which have, well, where the network is a large fraction of the cost, while on the smaller machines the network may perform?
So we try to make choices in the code that are backward compatible. We try to make the choices that don't hurt backward compatibility or hurt the performance on smaller scale clusters. One of the ways that we can do this in Flash is the architecture of the code. So we can have what we call sub-implementations of various code units, where the old code still exists in its pristine condition. But if you, in the build system, specify an option, new code is replaced. New code replaces that old code. And so you can write specific tuned code for an architecture that will then replace the old code. That's one way that we deal with it, and that's one way that we try to not break backward compatibility with older hardware architectures. It's not great because it leads to code duplication, which can be a nightmare. But it's one way that we have dealt with this.